If you haven't taken any of our program, it might be good to know how it's structured. So you'll have 3 days here. By the way, my name is Ramses van Zoon. I'll be instructing this course here. This is me. Hi. So we'll have 3 days. The first day will be a lecture, so that's today. And then I'll give an assignment at the end of that, or a couple of exercises for you to play with, that you can ask questions about tomorrow in a hands-on / office hours session. And then at the end of that day, the idea is that you would submit whatever you have to the website. And that's really meant for us to just sort of see where everybody's at and to see that you've engaged in the material. And then we can use that to give feedback on the last day. And then I'll have a few extra slides as well to some final thoughts, a wrap-up session. If you are present for 2 out of 3 meetings and you submit the assignment, whether it works or not, but as long as we see something happens, that you did something with the material, then you'll get credits for this course, and you can accumulate credits until you have a signer certificate. The other thing is today we're going to use the Jupyter Notebook interface. So what you will need to be able to get on there is the login information from the website. By the way, we have a couple of helpers here. We have Bruno, and I think Alexia is here too. So if you have any questions, type them in the group chat. I might be too busy speaking to notice, but they will notice and answer your questions. And then every now and then they can interrupt me if something is really unclear. So as I said, we're going to use the Jupyter Notebook. To get that, you can go to the course website. And if you log in there, that's the same website where you signed up, so you should be able to log in there. Once you've logged in and you go to this course, there's a link called Login Information, and that will show you what your login is. If you have a Compute Canada account, that will be your login. If you have a temp account, so you log in with TMP_ something, you will have to log in with yet another account. It's called the Sign Guest account. But as I said, on the website, it should give you all the login information. And to get to the website, that's from the website to the Jupyter Hub, you should be able to just click the link that's there and then log in. So as I said, we're going to use a Jupyter Notebook. There's a notebook that is actually precisely the content of these slides. And so I'll show you how to get those. But for those, you'll have to be logged in first. And so any other details, here's the course website. So we could, let's see. So as I said, that's where you would go. Here's your login info. This is mine, so you won't see my password, but you would have a password. Click on this link and Jupyter Log and log in. And then once you're logged in, you should see something like this. Okay. So this is your files. I have more files. If you have a temporary account, there'll be no files. If you have your Compute Canada account on Signet, on Niagara, you should be seeing that. If you're not seeing it, again, just let people know in the chat, and they can help you out. So we're going to cover in this session things to do with high performance computing and Python. So we'll have to look at the performance aspects of Python. Python is a great language. It's very flexible. It's very easy to learn. There's lots of functionality in it. But it's not always performance aimed. So we'll look at how performance and Python go together and how they don't go together sometimes. And then we'll look at some profiling tools. Profiling is a way to assess the performance of your Python script or code. And then after we've figured out how to look at our code and how to figure out what is slow and what is fast, we can try and improve things. So the improving part is sort of the second part. We'll look at ways to make numerics with Python faster using NumPy. And we'll look at a few packages that you can use to compute in parallel. So use multiple cores on a machine or several nodes in a cluster to compute things in Python in parallel and making it faster. By the way, the attendance code, it's 6. So we'll look at these particular packages. I this is a fairly short workshop, so I've picked things that I know kind of work. But that's not to say others are necessarily bad. They didn't work for the examples that we are using here. So to get started, you're going to need this notebook. And so to get this notebook, you need to be logged into the Jupyter Hub, and you have to get the notebook into your home directory. So this is the command you'll need. So let me show you how it goes. I'm just going to switch. So remember, you have to log into the website. So click here, and then I type in the username and password that is here. That will get you into the Jupyter Hub. You should be seeing this. After you do that, you can start it. You have to copy files from somewhere that you don't have access to right now. So you have to open the terminal. So to open the terminal, you can open the new button here, and you go to Terminal. And now you have a command line on the Jupyter node. And so I'm in my own directory here. So pwd tells me where I am. This is my home directory. Your directory is going to be elsewhere. Let's see if I can make this a bit bigger. There we go. And the command you need to execute to get the notebook is copy and then -r, because we're going to recursively copy a whole directory. Signet course SS 2020, that stands for Summer School 2020, and then 7 HPC Python, one word. And I want to copy it somewhere. I have to give a destination. That's how the copy command works. And so I want it in the current directory, and that is done by a period. Now, it doesn't seem to do anything, but that is Linux for you. The directory actually now does exist. I can go into it. I can look at it. But I can also now go back to the tab or to the page where my file list was. So let me go. Hold on. Go there. Here we go. And you see the 7 HPC Python has popped up. We click on it, and in it is a notebook called Python HPC. So that's the one you want. If you click on it, you should get a notebook. We'll start it up. Will take a little while. It's a fairly big notebook. Just make sure that that's, there we go. So the command again, here it is, copy -r signet course SS 2027 HPC Python. And then I do $home because then I know it goes in home, but if you're in your home directory, that's when I did that period. So it's going to be nice if you guys can follow along. So I'm going to ask you guys to, let's say, raise your hand if you have managed to get that notebook. Okay, good. Lots of raised hands. Not too bad. So for those of you that haven't, okay, so let's take it one at a time. Okay, no, it's going okay. So if you're not able to log into the Jupyter Hub, because you are not seeing see, where were we? So if you're not able to log into the education side, that is one thing, and make sure you say what is not working. If you are logged in, but you are not seeing a username and password set in here, then something went wrong with us giving you a temporary sign-in account. Maybe you registered late. I don't know what would have happened. But then let us know that you don't have a temporary account, because we can dig one up later and give it to you, so that at least after the session, we can give you the access. If you have Bruno is saying it's the same credentials, only if you have a Compute Canada account. So I do, and so it says Compute Canada password. If it says sign at guests, then that's the one you should use. You should use sign at guests, 002 or whatever number you are, and then the password that would be listed here. You cannot see this unless you're logged into the education site. And likewise, you cannot log in here. You cannot take the attendance test unless you are logged in as well. If you can get into the education site and you cannot get to the Jupyter Hub, that would be strange. You should be able to log in and at least see your main files or something like this. So again, if you have trouble with getting the terminal, that one's here, new terminal, let us know that. So let us know exactly what is not working for you. If something's going wrong, if you get into the terminal, but you are not able to find the files in the terminal, then give us the exact command that you're typing, and we can see what is wrong with the command, because then it's likely a typo or something like that. I'll show that command one more time, and then I think I'll go on with the slides while we try and work out the kinks behind the scenes. There's my, yes. Okay, so I'm gonna just, there's a lot of slides and talking before we're actually doing anything, so you have some time to try and catch up, but that's the idea. Once you have your Jupyter notebook, you can open it up, you can follow along with these slides. By the way, the slides are also on the website as a PDF, like a one flat PDF. So you could also print those out, and the instructions should be in there as well. Okay, so if you're not following on at the Jupyter Hub, you're going to need some packages installed, which is why it's probably worth trying to install these packages. It's trying to use the Jupyter Hub so that you don't have to worry about installing these packages. But for the future, or if you're going to use this notebook later, you need NumPy, NumExpr, Matplotlib, line profiler, memory profiler, MPI4Pi, and multiprocessing to be using this particular notebook. The start of the notebook has all of these has import statements for all of these. So this is the first cell that you can execute in the notebook. Execute this to make sure that everything is indeed working. If there's any errors, then, well, if you're on a Jupyter Hub, that's not good. There should be no errors. But if it's on your own machine or another Jupyter Hub or Jupyter notebook, this should be working for everything else. Okay, so let's talk about high performance computing and Python, because there's a bit of an issue here. Python is a high-level interpreted and dynamic language, all of which are features of non-high performance languages. They're often at odds with it. And we'll see exactly why, but basically you pay for all of the convenience. It's a fairly easy and expressive language, and very, very popular, partly because of that, and partly because of the large number of packages that give you extra functionality that are available for Python. And so when you're using Python, developing a new code or a new computation can be very quick. It can be much faster than, say, in a compiled language, just because of the language itself and the convenience that it gives you. But it's not high performance, and there's a few main reasons why. Python is what we call an interpreted language. The way it's supposed to work at its basic level is that you give Python a command, and which is like a text format. It reads it, it interprets the syntax, it then figures out what to do because of the command you gave, and then starts executing this. And then it goes to the next line you enter, etc. And so there's a translation necessary from the Python code to eventually machine code that the central processing unit can execute, right? So that has to be done in any language, but the trouble with Python is it has to be done for every new line that you read. And if it turns out that you have, say, 10 lines, and what you do with line 2 is actually not even needed, or line 3 can be done before line 10, there's no way Python can know that. It has to do it in order, so it can't do any optimizations. And every time you hit a line again, in principle, it has to reinterpret that line. So the interpretation takes quite a bit of time. So that's on the basis of the interpret part. And it's not that there's no optimizations possible, but that is a bottleneck. And then the second bottleneck is the fact that Python is what we call a dynamically typed language. So the variables that you have in Python are not, don't have their names aren't tied to a particular type of variable. And what that does is that as Python is doing any computation, it has to check what type your variables are, because it can't count on this being a number or a string or a list. It has to basically check it. And if it doesn't work, it will have to give an error message. And so there's a lot of checking going on, while even after it's interpreted what you want to do, now it has to see if the things that you're calling make any sense. It has to take care of memory management. You don't have to allocate and deallocate memory in Python like you have in for instance, C++, but that happens behind the scene, and that's some overhead as well. And the way that things are stored, because the type is sort of part of the value, is that every time there's any sort of value, there is some field there that also says what type of value it is. And so that gives you a whole bunch of storage and also sort of streaming overhead. Like you can't just read a whole list of numbers. You read a type and a number, a type and a number, a type and a number. So those things are slowing down what Python can do. And they're in contrast with what we call compiled languages, where you also write all of your lines first, you give it to a compiler, it makes the translation to machine language, but it also checks whether there's any optimization. It also often has strongly typed variables, which means that if x is an integer at any point in the code, it's an integer everywhere, and it doesn't have to check that it is whether it is an integer every time it does something with it. So and that means that the translation to machine language is a much tighter one, and the machine language part has to do way less work. So we're going to look at two examples to discuss the performance of Python and to fix it when it's not working. The first one is it comes from physics. So it's a two-dimensional diffusion problem. For those of you that know physics and know a little bit of partial differential equations, this is the equation we're solving. X and Y are spatial coordinates. So we have a plate, basically. There's an X direction, that's one direction, and a Y direction. And on that plate, say, is a temperature P or a density P. It doesn't matter whether it's density or temperature for the equation and therefore for the computation, but I might switch back and forth. But let's say it's a temperature. Then the temperature varies over the plate, and it changes in time. So X and Y are the coordinates of the plate. T is time. There's a diffusion constant D that basically says how fast heat diffuses, and that's it. It's on a square domain, and so the way this is going to look when we solve it, just taking some snapshots, is kind of like this. So the top left one here is the original situation. You can think of it as a stove with 4 burners, and we've switched it on, and then they're all hot. So these are the 4 hot spots, and then we switch it off at time 0, and we see how the stove cools down. So after a little while, it's a little cooler. After a while, it's cooler still, and then slowly but surely, it will all die out to be a room temperature, which in this units is 0. So room temperature 0 here. So that's really what's happening in this simulation. That's all that the math does. Okay, so the math says that we have to know this density field, or this temperature field, in every point possible, every xy possible. That's an infinite number of points, and computers don't like infinite numbers. So what we do is we discretize this problem. That's how you numerically solve it. So you discretize in both x and y directions. You take points certain spacing apart. We'll call the spacing dx. We'll take the same spacings in x and y just to keep it simple. And then the derivatives that are in this equation become finite differences. So the differences between neighboring points. We have to compute those differences. We get the right-hand side. With the right-hand side, we can do an explicit stepping to get the density at the next time. So we have the situation at time 0, say, and then the next situation will be at a slightly later time. Let's call it dt, and that's what works. So sometimes a picture makes a little bit more sense. So if we discretize really, really, really coarsely, we have this is probably something like 16 by 16 points. Each point has a temperature, right, as indicated by the color. What we have to do is we have to find the difference between a given point and its neighboring points in a particular way, and that difference determines how much it cools down. The more difference there is, the more it tends to cool down. That's how diffusion works. And so we have to compute all of those differences and then compute what the situation is at the next time step. So it's discrete in space and time. The more discrete we make it, so the finer our grid is, the better the approximation to the actual equation we want, but also the more points we have to do, and therefore the slower it will be. So there is a balance there of the number of points versus how accurate the solution is. So we have to set some parameters. We're going to have to play with them a little bit to say how coarse the grid is, how long we want to simulate for, etc. So they're all going to go in a file that's called diff2dparams.py. And the file is generated in the notebook. You can generate files in the notebook on the fly with this %% file magic commands. So you give it that command and the name of the file, and whatever follows is put in the file. So that's great. So we set the value of the diffusion constant, which hardly matters in this case. So we just set it to 1. A range for the x values. So we're going from -10 to 10. Say it's a very small burner of 20 centimeters across. How long we want to run this for. And obviously the units are pretty arbitrary here. So that don't take that too seriously. But say it's 15 seconds. And then the dx is how fine the grid is. So we have a total dimension of 20 centimeters. Then we have 0.075 centimeters for each pixel. We can also say how often we want to see some output. So as the simulation is going to go on, it will dump the time that it is and the picture of the simulation so far. If we want to do proper timing, we might not want to spend too much time on the reporting. So we make that only 3 reports at 0, 7.5, and 15. And then we can say whether or not we want these graphics to be generated or not. Graphics take quite a bit of time because, again, you have to basically compute all of those pixels once more just to give them a color. And so for good timing, switch off the graphics. The way this has been structured is by giving extra semicolons which do nothing in Python. We can also read in this file in C++, and it will still work and give us values. So by that trick, the same parameters that will be used in Python will be used in the C++ version that comes with the notebook. So let's see how the two compare. So the same algorithm has been implemented both in C++ and in Python. The C++ code is in the directory that you copied, so that's 7 HPC Python, and can be compiled with a command called make. We are not assuming that you know C++ here. We just want to show the difference with Python. So there's a command called make that will do this for you. And that also can be done from the terminal. So in the terminal, we are going to time how long this takes. We can do that with percent time. Any cell you put percent time in front of or at the start of will give you at the end how long things took. We're going to be very concerned with timings all throughout. So that's that. You'll see lots of percent times. And then we can change a whole cell into something that runs in the terminal. And on our systems, that's a bash shell. So that you do that with percent bash. And then because we are on a supercomputer where you have no software available until you load the module, you're going to have to do module load, GCC, pgplot, and RRA. GCC gets the compilers, pgplot gets the graphics, and RRA is a way to do arrays in C++. That's just to make it work on this particular computer. Then basically you can type make. I'm a bit more specific here, but make will do exactly these commands. It'll use the compiler to compile the code, create an executable, and all of that takes a couple of seconds. So the compilation is fairly quick of this code. And then once we've compiled it, we can run it. So this code can be run again in a bash cell. We'll have to load the modules again because each shell starts anew in the Jupyter Notebook, unfortunately. So we'll have to load those again. And then we can time how long it takes to run it. So the executable that is created by the make command in this case is called diff2d_cpp.x. So make sure you type everything carefully, but it's already in the notebook, so you should be okay. And so then with the time command in front of it, it will actually tell you how long it took. Let me just see. I see people have some issues with compiling. So let's just try it. Let's make sure that this works. Let's see. So I have, is this the empty one? Yes, okay. So first cell to go through is all of the import statements, and that pulls through. You can see all the slides come by. You have to create the params file. That seems to have gone well. And then we should be able to compile the code. That worked well. Module loads units all worked. And then we're going to time it. Yeah, that seems to be working just fine. Let me see. What directory am I in here? I'm seeing a header file is missing. Yeah, no, that header file should come from the module though. If you want to debug this a little bit more, it makes sense to cut these things in half or in bits and pieces, to just do one at a time. So try to make sure that the module load, so module load GCC, pgplot RRA, and then type module list to see if they actually were loaded. And this is what I see, and you should be seeing that. If you can't see that, then that's an indication something went wrong. And it sounds like with all those missing directories and files that's the issue. What's the output of module list for you, Matthew? Ah, oh, that's interesting. I didn't think of that. Okay, try changing it to this. Maybe the old ones are broken. There's a newer set of modules in Niagara called NIA 2019B, which is where I checked this with. So try, instead of module load, just GCC pgplot NRA, do NIA 2019B before it, and then that should work. Let me try it the opposite way also to see if I get your error. Yeah, that's weird. It looks like the old pgplot module is broken. Okay, sorry about that. So yeah, the NIA 2019B seems to be fixing that, which is for me the default, but not for you guys. Sorry about that. I had no idea the old pgplots module wasn't working. Okay, good. And that's no. I'm not getting back to, here we go. Okay, so somebody asked what these numbers are. Remember, we're doing a runtime of 15 and it's doing it in steps. And we asked for output every 7.5 time units. So it's basically saying when it prints 0, it says I'm at the start of my simulation. When it prints 7.5, almost, it's in the middle. And when it's at the end, it prints it out. The reason it's not exactly 7.5 and then 15 is that the time step isn't exactly the 7.5 can't be divided exactly by the time steps we're taking. So this is the closest it can do. So this tells us that it's progressing, and we have only 3 numbers because we set the out time to 7.5. So the C++, make sure you do a make clean before you do anything else. So when you change the modules, you have to do a make clean to make sure that everything that you had from the old modules are gone. Yeah, make sure the make clean is very important. Okay, so the C++ code takes about 1 second to run. It took about 2 seconds to compile. If we had the C++ code, I'd be pretty happy. But suppose that we started from the Python code. It's the same algorithm. How long does it take? And so the code for that is in diff2d.py, and we'll look at it in a second. And I can run this because it's Python code within the notebook. But then I have to make sure that the parameters are properly imported. So the parameters we put in diff2d params.py, and by running them, I get those assignments done. So after this, the variable d will be set to 1, the dx will be set to 0.075 or whatever we had set it to, and then diff2d will take those parameters and run it. So I ran that, and you can do it in the notebook too, but I should warn you, this is going to take about 5 minutes. So the timing, because we do percent time, we get the timing, says that this took 5 minutes to run. It's the exact same parameters that on purpose. It's the so this and the exact same algorithm. The for loops are the same, the expressions are the same, just the syntax of C++ has been converted into Python. So that's not very good, because that actually means that the Python version of this code, pure Python, just a straight translation of the C++ code, is between 200 and 300 times slower. Depends a little bit on when you run it and where you run it. And that is not very promising for using Python on HPC. You do not want, you don't want your PhD project to take 800 years instead of 4, right? And if that's the case, this was all, I would just say, well, this is the end of the HPC Python session. Go and learn C++, everybody. But we still bother with Python for some reason. And one very important reason is productivity. See, if we look at the Python code in diff2d, it's actually fairly small. I tried to put it on the slide, and that does not work. So let me go to the notebook. So here's the code, and let me just for a moment make the font size a little smaller so we can see most of it. So we have a little doc string that just explains things, and then this is it. This does the whole correct numerical simulation of and numerical solution of this partial differential equation. There's some list with points. There's a density in there. Density is the variable that takes the place of the p variable in the equation. There's an initial condition that's set. Graphics is in there. And then we just start computing right-hand sides and taking time steps and even there and then plotting. This is all. And you can look at the C++ code, and it's not terribly long either because it's a fairly simple problem. But still, this is why we bother with this. The plotting is in a separate function. So if you look carefully, you see the plotting is called here if graphics is switched on. This plot length function is separate, and it's separate and it's different in the notebook than it would be in a standalone situation, just because the interface is different and the way to get images to show is slightly different. But it's still not that big. Okay, so one thing that I'd like to show, because this is going to be annoying for some of you, this idea of modules and loading modules, there is a way to load modules in the Jupyter notebook as well. I'm only going to show it and not actually do it because you'd have to close your notebook, etc. There's this tab called softwares, and you could select the modules that you want. Then afterwards, restart your notebook, and it would just have those loaded all the time. You wouldn't have to have those in your you wouldn't have to have the module load commands, but yeah, I kept them in because then this stuff works more generically. Okay, so we have this separate function, and that's it. We have a fairly concise code. We could easily change it if we need to change the algorithm. It's fairly easy to do. So we can play with parameters fairly easy. You can make a movie, and let me show you how that goes. That only works in the notebook, but once we're there, so let me make sure I have defined the diff2d and the dense. I'm not going to run this because I know it takes 5 minutes. Oh no. So this little code here reads the same parameters, but then actually feeds in slightly larger dx's and sets the graphics to true. And the larger the dx, or the larger the grid spacing, the faster things will go. So it won't take the 5 minutes. It'll just take a couple of seconds. And we can see it happening. And that's the other nice thing about Python. Doing graphics in it isn't terribly difficult, and it's still portable. And so I can see if what I did was actually sensible or not. Okay, so the slides only show the end of the movie. That's not very nice. So it's a nice way to play with things, to prototype things. But now we're still stuck with this, right? So we can easily write some code. It's very flexible. There's useful packages. It's relatively easy to use. I can throw graphics in there. That's great. But there's still this performance hit. And I don't want, if I'm doing an actual research project, I don't want my computation to go 200 times slower than it needs to go. Right? Now, I chose the diffusion equation for a reason. It's about the worst thing I can do to Python. I am really squeezing it where it hurts, because this dynamic and interpreted nature of it really comes out when you have what's called tightly coupled calculations. So I need the neighboring points of every point in that grid, and I know they're all double precision numbers, but Python doesn't know that. So it's constantly checking what type those neighbors are, and it's doing a lot of work that in a compiled language, the compiler would say, oh, I already see what's going on. I'm skipping all those checks because I see from the start that they are not necessary. Now, if you don't have such a tightly coupled calculation, or if you're doing a lot of file reading or text comparisons, or you're calling libraries or packages, Python packages that depend on compiled libraries, so the libraries might be written in C, C++, or Fortran, then those libraries are as fast as C, C++, and Fortran. And if that's doing most of your work, you're fine. So if you're doing, say, machine learning, and you're using scikit-learn, for instance, and one of the functions in there, they go to a compiled bit of code, and it doesn't matter that Python is slow because you're actually not really executing Python code. What it does mean, though, is that even if it's not always that bad as it is here, just because it's bad is a bad reason to go parallel. So don't solve a performance hit of a factor of 200 by asking for 200 times more cores. That is incredibly wasteful. Your HPC center is not going to like you for wasting time on a Python computation that could be done in C++ in like a second, right? You are also going to hit yourself over the head because you're going to run out of whatever allocation you have. It's just not a good idea. So the first thing we have to do before we're going to talk about parallel Python is performance in general. So how are we going to change or improve this enormous hit in performance? We need to know that. I have a second example, which won't be used that much in these slides, but is going to be useful for the assignment. Because I know not everybody has a physics background and some numerical background. This is a simpler case that will still illustrate most of these things. We're going to do an integral. We're going to basically compute the area under a curve. This is the integral we're going to compute numerically. So we have a function 7/10 x cubed minus 2x squared plus 4. And then we need to take the integral from 0 to 3. It's all very obvious why it's 0 and 3 because it's all arbitrary. So that's we can do an exact answer, so it's always good to know what the answer should be to make sure we did it right. But basically what we're computing is the area under this curve here. So if a curve from 0 to 3, it goes around like that, and it has some area under here. That's what we're computing. And this is a little Python code that creates this. How are we going to compute that? Very simple. We can't do infinitely many points. The integral says infinitely many points. That's not happening. We sample points. And the number of sample points is called n tot between 0 and 3. And then we compute those x values on that grid. Then we compute what the corresponding function value is. We add them up. We multiply them by the spacing dx, so the spacing between each grid point. That's a way to compute an integral. There are slightly better ways. We don't care. We're going to do simple, sum up the values of the function on a grid. So that's very simple to do. This area under the curve or integration computation. It's so simple that even the C++ code can just be put in a cell in our notebook. So we're going to create the code for it, auc.cpp, in the notebook. This is all it is. If you don't know C++, fine, just believe that it does what it does. You can kind of recognize the function in here, and it will print out what the answer is. And then we can compile this. Now you only need to load module GCC. That should probably work regardless of NIA and for not. We compute it. I put in a few flags. When you have some time, you can play with this. These are optimization flags that give the compiler the permission to use the CPU as best as it can. You don't have to have them. The times are going to be slightly different. So I would suggest you do take these. Just to be sure, if you're typing this yourself, this is a minus sign, this is a capital O, and this is the number 3. Then the Python code is just a function. We can keep that function in a notebook. We don't have to put it in a file. And it does the same exact thing, but you might be able to read this a little bit better. So the dx, the spacing, is 3, which is the size of the interval divided by the number of points. We're going to accumulate in A. We're going to compute what x is every time. And we're going to compute what y is. So that's the y value. And then we're going to sum them all up. multiply by the x, and Bob's your uncle. So let's see how that does in terms of timings. So we're going to take the same number of points in every one of them. We're going to take what this is 100 million. You do not need 100 million. Okay, I'm well aware that about 100 is more than enough to get an accurate result here, but then our timings are going to be so short that we can't see the difference. So this is just to illustrate the difference in speed should you ever have an integral that needs that many points. In the C++ case, so ntot is ntot, still the same. I'm going to time how long it takes to run this, and it's going to be 0.16 seconds. And then I'm going to time how long it takes to do the function. So we did % bash before. The exclamation mark is basically the one-line version of % bash. It runs something in the shell as well, if you weren't aware. And then the time command is a bash shell command to time things. Not surprisingly, we saw that one before, I think. So here we go, 0.1 seconds. The area under the curve function in Python takes 24 seconds. Now, if this is the only thing you have to compute for your project, then fine, you're done in 25 seconds. But still, the Python version is 160 times slower than the compiled version. So if this was an actual computation that took some substantial time, you don't want that. And even if you count the compilation time for this code, we're still talking about 25% slower. So that is not great. And we want better performance. And so we will you will use this area under the curve code and function to try and improve things and to find out why it's so slow. But first, we have to figure out what parts are so slow and how come it is so slow. So the only way to do that is to measure the performance. We have to know how to get to the hotspots in our computation. Where is all this time spent, right? And so by performance, it sounds ambiguous. It really isn't. The computer is doing work and it's using resources for that work. It's using CPU power, so it's actually the CPU is computing things. It's also using memory, store stuff in memory. If you're using distributed anything, it'll use the network. If you're writing to a file, that's another resource. What you want for performance is that you minimize all unnecessary work. So if you write 100 files and you needed one, that's unnecessary. That is underperforming. But then at the same time, once you're not doing any unnecessary work, one of these resources should be maxed out. If not, there should be something you can do to get more work done by your computer. Now, it doesn't always have to be CPU power that is maxed out. In our examples here, it will turn out that it is that. But you could have a system that is really large and needs a lot of memory to be stored. And then in that case, your memory limited rather than CPU limited. And that can happen. And that can still be like optimally performing because you need all that space, all that memory. So one resource is maxed out. But right now, all we're seeing is a long time. And we don't know where it's spent. And the last thing you want to do is be very clever and attack a small portion of your code that you think is the bottleneck, optimize it to pieces, and find out that that was just 0.001% of the computation. So you wasted a week optimizing something that makes no difference. You need to know where to focus your energy to improve the performance. You need to know the hotspots of your code. And there's a little quote of Donald Knuth, who's famously said, premature optimization is the root of all evil. The idea is if you think you're being clever by optimizing something, or you just guess where the bottleneck is and you start wasting time, you're going to make your code more complicated for no good reason, and basically in the process might actually do some damage. So for an effective optimization, we need to measure where our CPU cycles go, right? And so we'll first look at just time, like where is all this time spent? What part of the code takes that much time? And then afterwards, we'll also look at memory performance. In some situations, it's very important to make sure you don't run over memory limits, and if you do, to know where all this memory is used. Okay. Now, that just will tell us where the hotspots are. It doesn't tell us what the trouble is, but if we don't even know where the hotspots is, then we are nowhere. Before we go into finding the hotspots, a few notes on Python interfaces, I've called them. Basically, there's a variety of ways in which us humans can interface with Python. Originally, Python is a purely interpreted language that takes a line of code and interprets it. So that's the original Python command prompt. I don't know if you've ever seen one, but you type Python in a terminal and you get a prompt and you can type Python codes. That's fine. That's one way. It was, or people came up with a more interactive way to do this, adding things like history and remembering output and stuff. That was called IPython. Right now, that has more or less been superseded by Jupyter Notebooks, although I still kind of like the IPython interface. They run in a web server. Well, no, they run on a server. They're displayed in a web browser. And so there is a specific setup necessary for this to work, but then we have this nice interface where we can go back and forth and can do things interactively and add text in the middle. And then there's a fourth way, which is running scripts, which is similar to the command prompt, except you're just giving it one file and Python has to execute all of those commands. Okay. And the reason that I make this distinction is depending on which mode you're working in, the way that you get the performance out is slightly different. And so what I focused on here is scripts and Jupyter Notebooks for those tools that allow both. And the reason I'm doing both and not just Jupyter Notebooks is that in HPC, when you're running on HPC hardware, you're going to run scripts. You're not going to run in Jupyter Notebooks because it's interactive. And interactive, what that means is that most of the time, a human is just staring at the screen and typing things, and the computer is doing nothing. So that's also not very high performance. So people like to write scripts and run thousands of them and get the results out, and they run without them looking at it. So that's the pure running scripts. And that's what HPC workflow looks like typically. Okay, so time measurement tools. We already saw a few. We saw the percent time magic command that only works in the Jupyter Notebook, doesn't work in general Python. And it can either measure how long a single command goes with just percent time, or a whole cell in the notebook with percent time, which is great. And then an equivalent command for the bash shell, which was just called time. So you'll often see exclamation mark time and then the command, or percent bash and then time. And the reason that you want to do that sometimes rather than just percent time is that it takes some time to just start the cell, and that basically doesn't entirely tell you the truth on how long just the shell command took. So it's a bit more precise if you're doing shell commands to use time rather than percent time. There are extra commands. We'll see it at least a few times, called time it and percent time it. They repeat the measurement. So in a sort of a measurement methodology, that's much better. They'll tell you how often they measure the same expression and how long it took. They'll take an average. They'll give you an error bar. And for a lot of cases, there is some variability in how long things take. Other things are also going on your computer. If it's your own computer, it's because the operating system and your web browser are doing other things. If it's on a shared machine like the Jupyter Hub, other people are also running stuff. And so times can vary a bit. And so to get statistically relevant measurements, time it is really good. But if it's taking already 5 minutes, we're going to just stick with percent time because we don't want to do 3-5 times the same long calculation. Okay. One thing that is wrong kind of with all of them is that they take either a whole command or a whole cell, or maybe a whole script, but it doesn't tell you where inside that cell the trouble is. So it doesn't tell us the hotspots. It just tells us whether it's slow or not. So we'll need extra tools. One of those tools comes with Python. It's called C profile. You can use that package just standalone with scripts. You can use it in Jupyter Notebooks. One thing that you typically want to do when you're doing profiling, as I said, we just had a case of something that takes 5 minutes to run. If every time we need to do a profile, we have to wait 5 minutes, that's annoying. So you tend to try and make your problem smaller so that it runs in a relatively short amount of time. some smaller representative case. cProfile profiles functions. So if your code calls other functions that call other functions, etc., it will tell you exactly how much time is spent in each function. It doesn't go line by line, it just goes function by function. And so your code that you want to profile should be modular. That is, it should be separated in functions, and those functions should call other functions, etc. But we can try this. We're going to try this for our diffusion equation. And I'm changing the parameters. The dx is substantially bigger. The graphics is still set at false. The % file can override a file, as they will tell you that it did that. But it's good to know that it tells you that. And then we want to run the code. We can do that from the command line. So cProfile can be run this way. So the code was in diff2d, and it gets kind of longish, but in the shell, we're running Python. We're running it through the cProfile module. And then this is an extra parameter that just says sorted by cumulative time, so that rather than just the time in the function. Now, it gives outputs. It gives a lot of output. Because we've sorted it, the most important part tends to be on the top. You can see the total time spent in it, and the largest total time here is spent in diff2d.py main. There's a main function, and that's where it spends all its time. In the notebook, you can do a similar thing. You can use the magic command %prun. It looks similarly. I just first have to run the parameters so that they're loaded again. Otherwise, the old ones would hold. We wanted the coarser simulation. And then we prun. Here's that same flag again, just to say sort by cumulative time. And then you can give it the function or the command you want it to profile. So in this case, it's just diff2d main. That was the name of our function inside the notebook. And it gives a very similar output. The way these things are run, they're now called from within a cell. So there's a few extra different notebook-specific functions that pop up. But nonetheless, we all see that all the time is spent in diff2d main. So that doesn't tell us anything, but we could have known that because we've written only one function, and that function wasn't calling any other functions. So we asked cProfile, I have one function. Please tell me where all the time is spent. And they're going to say, well, that one function. So, excuse me. That's great, but useless in this case. This is not a modular code. cProfile is not good enough. We need something that can tell us line by line where things are met. There's a good question by Joseph. What's the difference between total time and cumulative time? So if a function is running like diff2d main and it calls another function, then the time that it spends in that other function that it calls could either be counted as also being in the first function or not. So basically, it's either including the time of functions that are called within the function or not. So the cumulative time is basically kind of what you would think, like how long is the time between entering a function and exiting a function. That includes all of the time spent in subfunctions. The total time subtracts those subfunctions, and so only counts the time that you actually spend in lines of code that are in that function, not in lines of code of functions called by the function. Does it kind of make sense? Okay, good. And so it's important, the total time is very important, but it really depends on what you're looking at, really, to see the bottlenecks. Sometimes you don't want to know that most of the time is spent in this plus operator function or something, because you already know you're doing a lot of pluses. You don't want to know where they were done. So the cumulative time is often the ones that I'm interested in. Okay, so line-by-line profiling is possible with another tool, and it's called Line Profiler. It's a separate module, a separate package. If your Python doesn't have it, you'll have to pip install it, but it's pretty standard. Again, you do it on a smaller representative case. The thing that you have to have for Line Profiler is you have to have your function in at least, so your code at least in one function. So you can't profile just like if you had a script and it had no functions at all, line profiler can't do anything. And the reason it can't is it's going to take any function you have or any function you tell it and decorate it. And it'll decorate it, or you have to decorate it with add profile in front of the function. And that will basically take that function and turn it into a profilable function. So by default, line profiler can't look into their functions. Only C profile can do that. Line profiler can. Putting add profile in front of it magically makes it accessible to line profiler to profile. For scripts, this is what you would do. So you have a script, any function you want to profile, you put add profile in front of the def command, and then you run your script through a special command called kernprof. There's a couple of useful flags here, but anyway, that's what you would use. And so here's the same example as before, diff2d. We're running it through kernprof. The -v says that we actually want to see the results of this of the profiling. And so that it's running, it will first show the output of the actual command, and then we'll show the profiling. And so it says, well, I wrote the profiling results to this file, and the timer unit was 1 microsecond. So that's what? No, we didn't get anything out of here. We got timings every microsecond, and we got no output. And the reason is that we didn't change the function in diff2d.py. We have to put add profile in front of it. And now, to automate things, there is a cell in the notebook that does this. It uses the set command. Set is a Linux command that is very powerful. It can replace bits and pieces in a file and put them in another file. So I've done that here, but really all you need to do is just open that file, diff2d.py, and put add profile in it. So once you've done that, you would have, instead of just def main, you would see add profile def main. Okay, that's the only difference with what was there before. That, as I said, turns the main function into an opaque function, from an opaque function into a function that line profiler can look into. So now when we run kernprof -l-v and the name of the new script, we get the same output as before, and then we actually get some profiling information. Now, on slides, this looks horrible because it's all wrapped around and it goes on forever. So I'm going to switch to the notebook. Let's see where this is. This one, habits. Go to here, this one. Measuring performance. Here we go. That's the C profile. That gives us nothing. Lots of functions have basically 0 time. The top is the part that matters. Line profiling. Here's the missed results. And here we go. Now, so kernprof writes all of these things. You can make the font a little smaller just so you see what the supposed output looks like. So on the right here, we have the code. And on the left, it tells us what the line number is, how many times it was hit. So if you're in a loop, it'll hit us many times. How much time is spent in them, and how much per hit. And so we can see, just scanning through, that we have a large time spent here in this line that starts with Laplacian and with tens next here, but also fairly large time, almost the same amount of time, just doing the for loop over j. It's hit a lot of times. That makes sense, I guess, but it's also taking a lot of time. So it takes about the same amount of time, or a complex amount of time, to loop as to compute. And keep that in mind. There's a second way to do this in Jupyter Notebook. This was on the command line, so the exclamation mark means you're in the shell. You have to activate the line profiler magic. The command is %lprun rather than prun, but you have to do load x line profiler first. That's already in the notebook, so that should work. And then you can do lprun, and you have to specify what functions you want to trace. So in the notebook, we haven't put add profiles anywhere, and we won't have to, We can have LP run do that for us, sort of dynamically, but we have to tell it which functions those are. So the diff2d main was a function that we're going to call, and we want it to be decorated. That's what the -f do. If you have several functions you want to decorate, you do -f function name, -f second function name, etc. And then at the end, you give it the expression you want to compute, much like prun, and it gives you essentially the same result. And now, depending on whether you like this or not, in the notebook, when you do this, where's my notebook? Let's see if this works. This is the wrong notebook. What happens in the notebook, I'm just going to tell you rather than trying to fix it. In the notebook, rather than it popping up inside the cell, there's a second panel that opens with the output of the profiling that you can scroll through separate. So it's kind of nice because it gets long. And this is the case. I mean, it's understandable. You write your code with a certain width in mind. Now it adds columns in front of it. It's going to be too wide, right? So that's okay. Okay, so that's line profiling, which is great, very useful. We already see that in the computation of the dense next and the Laplacian, we're spending a lot of time and in those loops. So we already found our hotspots, and we're going to attack those in a moment. Memory measurement tools are also quite important. Memory is not important until it really is. And when you're running out of memory, what can happen basically is things just crash. Like your application crashes, your computer might start using the hard drive, so you get this nice spinning, your fan starts running. If you don't have a hard drive, and you say, how can you not have a hard drive? Many supercomputer centers don't have hard drives in their compute node. It just crashes, and with often very little indication as to what happened. So if that's the case, or if you suspect it's the case, it might be Python. And so how do we figure this out? Now, there's a few tools you can use to track memory measurements, even without it being Python. And I think I should mention those. They are Linux specific, but we're running on Linux right now, so that's OK. One utility is the top utility. If you type top, you get a list of all of the processes running on a machine, on a computer, ordered by how much CPU they're taking, or if you want, ordered by how much memory they're taking. You can just do your processes, if it's a shared machine, by top-u$user. And you get an output that kind of looks like this. Again, it's a little wrapped over, but you get how much memory things are taking, whether it's running, what the name is of the command. And so it's very useful, and it refreshes every 3 seconds. So you sort of get a dynamic view of this. So that's very nice. There's htop, which is purely interactive. I can't even get a I can get a snapshot, but I can't make it just print out one. It's more interactive. It shows more details. You have to run it in the terminal, but it has a similar purpose to see real time what's going on with CPU and memory usage per process. So this isn't delving into anything. It won't tell you what line it's in or anything like that. Just overall usage. And then if you're wondering about whether you're running out of memory, sometimes a very simple tool is all you need. There's a command called free. You can ask it how much memory is free. So here I'm asking how much memory is free, give it in megabytes, please. That's all that -m is. And it says, well, the total amount of memory on this machine is 1 terabyte. And you've used about 17 gigs. And so this much is free, etc. Very simple. But if you now want it line by line for your Python, you can do something very similar to line profiler, and it's called memory profiler. And that can be very useful to catch unexpectedly large memory usage. So you need the same instrumentation as a line profiler. So if it's a script, you have to put a profile in it. So we already did that for our commands. Yeah, so all these, the Linux commands I said are all for just that one single node. If you, there are tools to do performance analysis on your jobs, and I can mention them later. They're specific for supercomputer. Not every supercomputer has the same tools, but those are separate. These are just for a single node or a single computer. Okay, so we're going to run, what's going on here? Yeah, so we're going to run our code now through the memory profiler. And it works very similarly. On the command line, you would have to say python-m memory profiler and then the name of the profile. And it gives a very similar looking output. And again, my apologies for the wrapping around. It tells you what line you're in, how much memory is used, and how much memory is added to it because of this command. So if there's a command that say allocates or creates a large array, you would see a large increment here. But at the same time, you can track memory usage. So if this slowly increases throughout your code, you know you have an issue. Here too, there is a notebook version of it. It's called %mprun. This one's a little annoying. I hope at some point they fix this, but it can only work if your function is in the file. So rather than line profiler, which just takes a function that's in your notebook and automatically basically wraps it into an add profile, this doesn't work that way. And so we have to put it in a file. I wrote a little hack for the aficionados, figure out how this works, but it basically writes the function to a file and then reads it back in, and now it's a function that was defined in a file. The result for this is essentially the same. So it writes it out to a file. It read it back in. Now I'm running it through mprun. Again, I have to say what functions I want to decorate, and then the command, and it shows how much memory was used and how much was added. And very little interesting is going on here for this code. In the sort of resolution of measurements, nothing that is less than 100 kilobytes even shows up. So it looks like nothing is happening at all. Something is happening, but it's very small. Yeah. Okay, so we can now find both how long things take, where they take that long, and how much memory they're taking. Let's discuss a little bit how we can fix things, because you're going to need that if you want to do anything of the assignments. So we'll look at NumPy first. And what is NumPy? NumPy promises better numerical arrays for Python. It's a package. It's a Python package. Most of you probably already have heard of it. And it's created partly because lists in Python are funny when you're doing numerics. They're not a very good data type for doing computing, and arrays are a much better choice. What's the difference between arrays and lists? Lists is a collection of items that can have anything in it. You can have a list that has a string and a number and a peanut, like anything could be in there. And that means that they do funny things. So for instance, a list 1, 2, 3, 4, and another list 3, 5, 5, 6. If I multiply, if I add those two, I do not get 1 plus 3 and 2 plus 5 and 3 plus 5. No, I get the lists appended, because they're just things, and you can't add things. You just collect them in a collection. And similarly, if I multiply a list by 2, I just get the list repeated twice. So those are not the kind of things I want to do with numerical data. And so we need arrays. Arrays would do numerical things better. So NumPy is what gives us those arrays. We've already imported NumPy on the top of the notebook as NP. And then NumPy can create arrays. They are different from lists. When you print them, you'll see, because it will say array. And very typical of arrays is that they are collections of items that are all of the same type. And if you've listened between the lines, you can already tell that it's going to help, because it means that this idea that Python constantly has to check what type a certain value is can somehow be circumvented, because there's only one check to do for the whole array. And that is true. So you can create arrays of zeros, of ones. You can say what type you want. So these are by default double precision floating point numbers. Here they've been made to be integers. You can have multidimensional arrays, so a 2x2 arrays of zeros. Here it is, no problem. You can create ranges, so a range from 0 to 4. Obviously, that is a range 5 because Python. You can create grids between, so here's a grid between 1 and 5 with 1, 2, 3, 4, what is that, 30 points in between, something like that, inclusive. So that's useful if you want like a grid of X ranges. Hey, I think we need that for the area under the curve. You can do steps, or you can say how many points you want. So for the linspace, if you want 6 points in between 1 and 5, here you go, 6 points. So that's just creating some arrays. But they also, they behave a little bit more normal because they do what's called element-wise arithmetic. So you can do addition of one array and another array. If they're the same size, you just get element by element addition. And the same happens with multiplication, but here is something to be aware of, because there's also such a thing as a vector product. And that is not the same as what happens when you do vector star vector. So when vectors are multiplied, like NumPy vectors, you get element by element multiplication, so you get another vector out. Okay. When you multiply a vector by a scalar, it kind of does what you expect. Every element of the vector gets multiplied by the scalar. But if you want a vector product, like a dot product or an inner product, the star doesn't do that. The vector times a vector would give you a vector, whereas a vector inner product vector would give a number. So there's another operator since Python 3.5, which is the @ sign, that gives you these inner products. So let's just look at an example. Here are two arrays made with a range. If I multiply them, you see I get element by element multiplication, 0 by 3, 1 times 4, etc. When I do the inner product, so the @ sign, it does 0 times 3 plus 1 times 4 plus 2 times 5, etc. Okay. Matrix vector multiplication is very similar. If you just do a star, it gives element by element multiplication, and it does funny things. If you want linear algebra style, use the @ sign. And especially with matrices, the difference is very funny. If you do a matrix times a vector with a star product, which is the element-wise one, you get a new matrix with these elements. Whereas if you do the @ product, which is a proper linear algebra dot product, you get a vector which basically adds each row. So they're not even closely the same. Okay, so suppose we want NumPy, because people will tell you if your Python code is slow, well, did you use NumPy arrays? Because they are fast. So we're going to see if that's true. So here's our NumPy array implementation. And so let's see, we've got linspace here. So X became a NumPy array. It was before just a list. Dense became zeros, MP zeros. Before it was a list of zeros. Dense next, which is the density in the next step. They sort of do a leapfrog kind of thing. Also zeros. These were lists before, but other than that, the syntax of NumPy allows you to use those arrays in the same way as lists. So when I want the ith and the jth element of a of something, then I can just use that. Okay. So let's see how that works. Oh, we're restoring the previous parameters to compare the timing. And OK, so this is the old timing. It took 5 minutes, indeed. So our diff2d main. We're going to now do it with our fancy NumPy arrays. So that thing was called diff2d slow NumPy. And I'm not going to do that live, because it turns out that this takes half an hour. So this grandiose idea of switching to NumPy is 6 times slower than just doing native Python. That's horrible. So I just want to stress for a moment. I can already see that we're getting close to time, so I think the solutions will wait for tomorrow, but that's OK. If I just use NumPy arrays in a straightforward translation of a C++ algorithm, The computation is about 1,000 times slower than the C++ version. So when somebody says Python is slow, you now know why. When somebody says, I don't know if Python is slow, you can tell them, well, have I got a counter example for you. So this is, and there's no, I'm not cheating here. This is true. Python is kind of slow if you use it in the same way as you use C++. You kind of have to understand what NumPy is trying to do and what Python is trying to do to write optimized code in Python. And it is possible. But if you just say, I'm writing Python code, you can find some HPC analysts that give you a disappointing look saying, that is not HPC, you should be using C++. And if this is the kind of thing that they're thinking of, they are right. But this is the worst we're going to see. It's horrible, but it's the worst we're going to see. This is our rock bottom. We're clearly doing something wrong. We need to figure out what is really so bad. And so what I'm going to try to do is explain what's so bad about this way of using NumPys, how to use it properly, and then give you a start with some of the assignments. And then tomorrow we'll start looking at parallel ways to improve things and finish up. Okay, so it's all about the overhead that Python gives. Okay, its interpreted nature, the fact that it's dynamic, isn't just going away because we use NumPy arrays. NumPy works well because they are arrays and they're all the same, but you have to use them as arrays, as whole arrays. You have to use these vector element-wise operations. If you don't, if you use for loops, every time you enter that for loop, it has to reinterpret that line. Like it's just, there's no escape, right? So be aware of for loops, or another way to say it is be aware of for loops, or say it a million times, be aware of for loops. It's the for loops that kill you. You have to do vector operations. So let's vectorize this thing, as people call it. So we've got our same NP arrays. Here's another NP array. Great. And now rather than doing, this fell off the slide. I don't think I have. Okay. We have to see the code. Where's the code? Here we go, vectorized. A little bit less. Good. Okay, so same linspace, number of zeros. These still have for loops, but it's just initialization. These are the time steps, so they happen every time step. And rather than having the for loops, I use what's called slicing. And so you'd have to figure out why this is really doing what it's doing, or sorry, that it's doing the same thing it was doing before. But rather than saying I want the element 1 x spots next to you, you take the whole array and you shift it by 1, and then you add it in that way. So these are whole array operations. There's no for loops in computing Laplacian. There's no for loops in computing dense next. And so we're giving NumPy all of the things that it should need just to do its proper job. Okay, so let's time that. So rather than having for loops, we use slices in the appropriate way. This is the old code that took 5 minutes, so not even a very slow one, but just a slow one. Now with the vectorized code, it is 5 seconds. So yay, right now, rather than having made it 10 times slower, we made it 60 times faster. And that is something to be happy about. This is the way you should use NumPy arrays. Use them as a whole array, and you can get a speed up. If you use them as if they are lists, you're not going to get a speed up. This is even not all that far from the compiled time, which took 1 second. So you could say, well, factor of 5 is still quite a hit. But on the other hand, maybe it's something that you're willing to do. If you can write your code in a day and then run it for 5 days rather than spending 2 months writing a C++ code and then running it in a minute, the first one is still better. So productivity might well win here. We're going to look at the rest later, but I want to skip to the assignments for those of you that want to start working on it, because it's time. So for the assignments, I'm going to go to the notebook. The assignments are all in the back, and they have several parts, so we can already do some parts now. So they're all going to use this area under the curve function, which is on the top there. And you should create a new notebook because we're going to ask you to submit that notebook when you're done to the website so that we can see that you worked on this. So put it in a new notebook and profile it. Use the line profiler and see for the, what was it, 100 million points, where does it spend most of its time? You might be able to guess, but you'll have cases where you can't. And so we want to see you use the line profiler to show where it is. And then the next part you can also already do is to vectorize this function. So let's look at a function for a second. That's amazing. There we go. It's a straight for loop, but we now know for loops are bad. But there's no arrays here yet. There's no list. So you're going to have to do a two-step approach where you first convert this computation into something that uses a list, and then change the list into doing NumPy arrays. If you're able to do it in one step, if you see how that goes, also fine, obviously. But you're going to have to use some sort of arrays to do array element by element vectorization, and they're not in here yet. So this takes a little bit more restructuring to cast in a array form, but that's the second assignment. So hopefully you guys can start on that and come tomorrow with questions about that. And then once we've dealt with those questions, we will just continue with the notebook. I'll explain once we've done our NumPy. At this point, we're in a position where we can say, well, we have a performance hit, but it's on a comparable order of magnitude. That's where parallelization might be something you could do. If you're 100 times slower than you need to be, you don't have to parallelize. You have to optimize. We can focus tomorrow on parallelization techniques of MPI, which is a lot of fun. The assignment is in the notebook, but what I'll also do is I'll copy them also on the website. I think on the right it says assignment and it doesn't have anything yet. I'll copy them over as well, and might even shoot an email to everybody for the people that couldn't be here, that they kind of know where we are in terms of the material. It took a little longer to get through than I expected, but that's okay. We do have 3 days all in all. So the slides, or at least the notebook PDF is there, and the slides are just a slidification of the notebook. There's actually a way to convert a notebook into slides. It's a slideshow thing. This is the first time I'm trying this, but I don't know if I'm going to keep doing it. But it does keep everything in one source, so that's nice. The code for the lecture today was 6. So if you came in a little late and you didn't know, it's 6. Any last questions before we call it a session? If you still have issues connecting and stuff, feel free to either email us, or there's a forum on the website too. You can post a question there too. Ideally, we'd all at least be set to do the hands-on when we start tomorrow. But if you still have questions there, obviously we will also address it at the spot. Okay. Well, then I'll hope to see you all tomorrow, unless the assignment is so simple for you, you have no questions at all. But others might have questions that you'd like to have the answers to. So do come.